Hello everyone, and welcome to the first article in my series on LangChain RAG tutorial. This video serves as a companion to Article 1, Quick Start Guide to LangChain RAG, available on medium.com. The link to the article is in the video's description. The article describes how we'll dive into setting up LangChain RAG and running our first RAG-based application. Let's get started. Let's start by visiting my article. You'll find the address in the video's description. Also note that the source code for this tutorial is available on my GitHub. First thing I want to mention is that this article was inspired by a notebook published by LangChain. LangChain have many use cases to use their library, and one of them is Q&A with RAG. When I started reading this material, I soon realized that all the examples on their own were working really well. But when you try to tie them together to create a real RAG application, that's where the problem starts. Now let's visit my GitHub. I'm going to be publishing every week. So this is the first article of a series of 6. One thing you're going to have to do is to clone this repo. You can do this by downloading the zip or just cloning using this address. I've put the command here a little bit lower. See, you can do a git clone to copy the repo on your local machine. I'm not going to cover how to do this because there's many videos out there that explains it, and I'm just going to concentrate on my tutorial. Also, if you want to support my work, you can visit the Buy Me a Coffee link and buy me a coffee or two. Now that we've downloaded the code locally, we'll be using Visual Studio Code to run the project. Now, a little trick to start the VS Code in the proper directory is to click here in the menu and you type cmd, enter. This will open a command line window, and then you type in code space period, enter. And notice how it opens Visual Studio Code in the proper directory right into our project. If you're enjoying this video, please take a moment to subscribe and like this video. This will help the YouTube algorithm promote my work and will encourage me to create more content. Thank you. Now that we've installed the repo locally, first thing we're going to have to do is install the dependencies. So since we're in a notebook, we need to put the % in front of it because that's a special character to say that this is a shell command. Okay, so I'm going to run this. It'll run for a few seconds. After that, we're going to have to load our environment because since we're going to be using OpenAI, we need an OpenAI API key. Okay, and this, I'm going to use the load.env library, and it requires a .env file. So in the .env file, we're going to have to, you're going to have to paste your OpenAI key in here. Now that pip install has finished running, you'll notice a note that states that we may need to restart the kernel. We're not going to take any chances, and we're going to restart the kernel by clicking the restart button in the ribbon. Once it's restarted, we're going to clear all the output. Okay. Now, to make sure that our API will work, we need to run the load.env to make sure that the OpenAI API key variable is set. So let's click the play button and make sure that you see a true here. Before I give you a detailed explanation and a code walkthrough, let me give you an overview of what we're trying to accomplish. So in this cell over here, we're going to load the different modules and classes needed to run this tutorial. So let's go ahead and run this. After that, we're going to be reading a blog post by Lillian Wang. The address is right here. Let me show you. It's a blog post that was published about a year ago. It's called LLM Powered Autonomous Agent. It's a pretty detailed article, and it's still actual. It was published on June of last year, I think. Yeah, June 23rd. Okay, so basically we're going to be using web-based loader, which is a web scraper that requires BS4. BS4 is bowl of soup, is another library used to scrape the web. And we're going to scrape only some classes, and I'm going to show you that in detail later on. Once we instantiated our loader, we're going to load that into a Python list called docs. Then we're going to split it into chunks. Once they're split, then we're going to create a prompt. The prompt is basically the question we're going to ask ChatGPT or the API. Okay? And we're going to pull the prompt from the hub. The hub is a repository provided by LangChain where you can find all kinds of components and tools, including pre-made prompts. And for this example, we're going to use the RLM/RAG prompt. Okay? Later on, I'll show you how to use your own prompts. Then we have a little function here called format docs, which is basically used to format our content for the context. Okay? Then we're going to instantiate our chain using the LCEL or the LangChain expression language. And once that's instantiated, let's go ahead and run this. It'll run for a few seconds. We can now run the RAG chain. Okay? Basically, we use the invoke command. So the invoke will basically call the RAG chain, and the RAG chain is using the LCEL syntax, which basically is piping different components together. So the first component is a variable name here called context, and it's calling our retriever. The retriever is basically what is getting the information from our vector store. And I'll explain that later on. Okay? Once we have the information, this information is passed into the format doc, which basically just pre's up the information. And then the question is a runnable pass-through, which I'll explain also later. Basically means that I don't have the question now, but once you're ran, somebody's going to send you a question. So the question is right here. So the question is passed to the prompt, which is defined by the pull over here. And the output of the prompt is sent to the LLM. And now the LLM processes the prompt that includes the context and the question. And that is fed to the output parser, basically removing all the extra information, and returns a string. Okay, so let's run the chain by using the invoke command. Should run in a few seconds. As you can see, all we have is task decomposition involves breaking down complex tasks into smaller and simpler steps, blah, blah, blah. Okay, what if I remove the output parser? Let me comment this out. Reinstantiate. And let's rerun it. And now you'll see my response should be different. Now I get an object called an AI message with content, and the content contains my answer. But I also have a bunch of information that could be interesting. For example, I have the token usage, 48 token, the prompt token, 563, and we have the total token, 611, the model name, and all kinds of other information. Okay, so more than often we're going to be using an output parser. So I'm going to put it back in because I don't want to deal right now with the AI message object. If you remove the comment in front of the output parser, make sure that you reinstantiate the RAG chain. Otherwise, if you run it again, you're not going to get the string, you're going to get the AI message object, and this tutorial for now needs to have the output parser. Okay, so make sure that when you run the chain that you get the string as an answer. Now that you have an idea of what we're trying to accomplish, let me give you a detailed code walkthrough. And let me start with the retriever. The retriever is what's responsible to query our database to find out which part of the blog post I should use to answer the question. So you might ask, why do I need part of the document? Why don't I send the entire blog post to ChatGPT and let it figure out? Well, the reason is that the way that it works is that you pay by tokens. And a token represents roughly 75% of a word. Okay, there's maths behind it, but for now, just imagine that if you have 100 tokens, you have 75 words. So, and you pay by the token. So if you have a huge document, you're going to pay for nothing. Okay, and not only that, depending on the model that you're using, there's a token limit. A few months ago, we had limits of, we call that context window. We had context windows of roughly 4,000 tokens, which is not a lot. I mean, if you take a PDF document, they can easily be, 10 megabytes. Okay, so how do you, why would you send a 10 megabyte PDF to ChatGPT when you can extract parts of the document? But now, how do you extract the proper parts of the document? Well, that's where the embeddings come into play. Okay, so when I instantiate my vector store, I need to say which embeddings I'm going to use. And in our case, I'm going to use the OpenAI embedding because they work really well. They work for English, Spanish, French. There are many embedding models out there. Keep in mind that using the OpenAI embedding is not free, but it's fractions of a penny. Okay, so it's not very expensive. So the way that it works is that when we read the article is loaded into a Python list, and this list is split into chunks. Okay, so let me illustrate this. So basically, I have different chunks. Okay, I have 1,000. So second chunk, third chunk, and so on and so forth. Okay, all these chunks are now encoded using the embeddings. What the encoding does, basically, it gives a meaning, okay, to each chunks. Well, if you're interested in knowing how the embedding works, there are plenty of videos out there that explain it. I'm not going to cover it in here. Okay. Once the chunks are loaded into the database, we say that they're vectorized. Okay. Now we can use a retriever to query the different vectors. Okay. So the way that it works, when I invoke my retriever, it takes my question, what is task decomposition, creates embedding out of the question, and then it compares the embeddings of the question with the embeddings of the chunks of the blog post. Let's give that a shot. Okay, so it gave me 4 chunks. If I did a keyword search, okay, let me see if I said find decomposition. It found 5. Okay, task decomposition. Okay, which one should I use to answer my question? Well, using the typical keyword search on unstructured information is not very efficient. This is why we need the retriever. For those that are interested, as of yesterday, OpenAI introduced GPT-4o, which has a context limit of 128K, which is huge. Okay, keep in mind that the bigger the limit, more expensive it becomes. Okay, so in our case, we're using GPT-3 Turbo. So GPT-3 Turbo has a context limit of, we're using this one here, so it has a context limit of 16K. Okay, so different models, different context window. Okay, so you can search on Google for OpenAI context limit, and you'll land on this page. Let's talk about the indexing part. The indexing is basically where we load the blog post into our variables so that we can split it. Okay, so in our case, we're using a web-based loader, which is basically a wrapper around BS4, which is BS4 is bowl of soup, is a very powerful web scraper. And in our example, I'm using a class attribute to limit the scraping to these 3 classes. Okay, so once I run this, my doc variable, which is a Python list, will contain the text of these 3 classes. Okay, let's look at the length. So basically, I have a list that contains some elements, and one of them is page content. Page content is the text that we scraped. We also have another one which is called metadata, but I'll show that in a second. So I have 43,131 characters that I was able to scrape from the web page. Okay, if I print the first 500 characters, you'll see that, that's the title, the date, and so on. Okay, So this is the starting point of my splitting. Okay, if I want to look at the metadata will give me the source. If I was reading in a PDF, I would also get the page. Now for creating the chunks. In our example, we're going to be using what is called a recursive character text splitter. What that means is that even though I'm asking for chunk size of 1,000 and an overlap of 200, the recursive character text splitter is a smart splitter. It's going to try and not to cut right in the middle of a word or in the middle of a sentence so that we would lose the sense or the context of what the meaning of the sentence is. Okay, let me explain. If I illustrate this with the page, if I scrape 1,000 characters, and let's just say 1,000 characters would happen right here. Well, it's smart enough to say, no, don't just do that. Stop at right here. Okay. But since we're using the recursive, it might decide that these two words, if I keep that without that, I'm going to lose some meaning. So it might decide to stop here instead. Okay. Now the overlap of 200, what does that mean? Well, it means that when I start the next chunk over here, I'm going to include 200 characters of the previous chunk, or roughly 200, because it's going to try not to cut in the middle of a word. So instead of starting here, it would start 200 characters earlier, let's say over here, okay? And then it's going to create another chunk of 1,000, okay? It's doing this because just in case that you're cutting at the end of a page and the beginning of a page, and the beginning of the page belongs to the previous page, so that you don't lose the meaning, okay? So you'll have to play with that a little bit so that it makes sense. But for now, we're going to use chunk size of 1,000 and overlap of 200. Some might say it's too big. You can reduce it. Just play around with it. Okay, let's give it a shot. What does it mean? So I'm going to run this. And now I have, remember, my original doc variable had one element of 43,000 characters, okay? Now I'm splitting it into a list called all splits. How many do I have? Now I have 66 elements, okay? So basically it took my 41,000 characters and it split it into 66. But you're going to say if you divide 41,000 by 1,000, it doesn't equate 66. Right, but don't forget, we have an overlap of 200, okay? So if I look at this, if I look at my first element, it has 969 characters. Why? Why not 1,000? Well, because it didn't want to cut in the middle of a word or in the middle of a sentence. Okay? Now let's look at the metadata. Now the metadata includes the source, but it's also giving us a starting index. What does that mean? Well, it's the position on the web page. Like if I wanted to give you a citation or the context, where exactly did I get this context? Well, you would see that it's at position 7056. Okay, so this is pretty important. In the next articles, I'm going to show you how to provide context and how to give citations, and the metadata is going to be very important. Now let's look at the store. In our example, we're using the Chroma database, and we're using the from document to create our embeddings. Okay? Why do we need to store the embeddings into a vector database? Well, because if you create a RAG application on, let's say, thousands of PDF documents, first of all, you're going to spend money creating all these embeddings. And you don't want to recreate the embeddings every time somebody uses the RAG application. In my tutorial, I'm using one blog post. But if you remember, it took roughly 7 seconds to scrape the web and create the embeddings. So, if you had hundreds and hundreds of blog posts that you wanted to feed to your Chroma database, it would take a long time. So what we want to do is we want to make that persistent. Okay, in this example, the Chroma database is not persistent. I'm going to show you in future articles how to make them persistent. But for now, just remember that we need to have a vector store to store our vectors so that we don't have to recreate the embeddings every time we want to query either a blog post or a PDF document. Earlier I mentioned the retriever, and if you remember, when we invoked the retriever directly, it only returned 4 chunks. We can change that. We can add an extra parameter called search quargs, and we can add the k parameter and change the amount of chunks that the retriever will return. We can also change the search type. There's similarity, and there's others like MMR. I'm not going to get into that. There's plenty of videos that explain that. So for now, the one that's important is the k, to change the number of documents that the retriever returns. So let's run this. Let's instantiate a new retriever. And now let's run it with a different question. So now how many documents? 6. Now that you understand how to load the data, in our case we used a web scraper, how to split it into chunks, and how to load it into a vector database, let's look at how we instantiate our RAG chain. In our case, we're going to use a chat OpenAI model, which is GPT 3.5 Turbo. Let's instantiate that. And then we need our prompt. The prompt is instructions that we use to tell the model how to answer the question. For example, you're an intelligent assistant, please answer the question using the following context, blah, blah, blah. Okay, so let's pull the prompt, and notice how long it takes to pull the prompt. See, 4.6 seconds. Earlier I ran it, it took 3.9 seconds. So I'm not a big fan of pulling prompts from the hub because it takes a few seconds. I prefer to hard code the prompts into my application, and not only that, somebody could change the prompt on the hub, and that would change the behavior of your RAG application. So I prefer to have my prompts hard-coded or in a database somewhere. So let's look at what a prompts look like. It's a chat prompt template object. It contains a placeholder for my input variables. It has some metadata, and somewhere in there we should have the actual prompt. Okay, see, you are an assistant for question answering task. Use the following piece of retrieve context to answer the question. If you don't know the answer, just say you don't know, blah, blah, blah. Okay. Now, what do I do with this? I need to format my prompt, okay? Because the prompt requires a context. The context, what is that? The context are my chunks that I'm going to submit to the LLM to answer my question. So I need to have a placeholder for the context and a placeholder for my question, okay? So I'm going to invoke my prompt, and that creates a human message. See, it says, you are an assistant for question answering task, use the following piece of information, blah, blah, blah. And I should have my question, I just use a filler here, and my context, filler, and a placeholder for the answer. Okay, so if I run this, this is the prompt in this particular example that would be submitted to the LLM for answering my question. Now that we've instantiated our prompt and our model, let's see how we can put our RAG chain together. And to do this, we're going to need to import some different modules like the output parser and the runnable pass-through. The reason we need the runnable pass-through is because we're going to use the LangChain expression language, the LCEL syntax, and basically that's piping different elements together. Okay? At first, if you've never used that syntax, it's going to be a bit awkward. But trust me, it's worth the effort, because once you understand the LCEL syntax, it's much easier to go from prototype to a production application. Okay, some people don't like it because it's not very Pythonic. Okay, it's hard to read. Okay, but you get used to it. Okay, now how does it work? Well, first, let's see my first component here is my context. Remember, my context was my input variable for my prompt. Okay, I have context and I have question. Now let's go back to the prompt and let's look over here. Input variable, context, question. Okay, very important. Because what that means is that this is a dictionary that is going to be passed as an input to my prompt. Okay, so, but before, it's going to call the retriever, get the context, and the retriever, remember, at first it returned 4 elements, and then later on we changed it to 6. So it should return 6 chunks that are going to be passed to the format doc. Why do we need this? Well, format doc is optional. We don't really need it. I like to use it because it inserts some line feed or 2 line feeds between each chunk. It's just to make it easier for the LLM to understand. Some LLMs will have a hard time if you just bundle all the chunks together. Okay, so just for clarity, we're going to insert some line feeds there. Then we have our question, which is another placeholder, but we don't have the question right now. We're going to have the question when we invoke the chain. Okay, so that's why we're using a runnable pass-through here. Okay, and then this whole thing, once it's executed, the result will be passed to the prompt. The prompt will then be executed just like we did earlier, but except instead of having the filler question and the filler context, we're going to have the actual question and the actual context. Okay, and that will be sent off to the LLM, and in turn will be sent off to the output parser to remove all the extra garbage around it and return just a string. Okay, so here's another benefit of using the LCEL is that once you've formatted your chain to use the LCEL, it's much easier to stream. Okay, for now, I'm just going to demonstrate the streaming because I'm going to have a whole article dedicated to streaming. Okay, here I'm just giving you a teaser that or an incentive to use the LCEL syntax, because I'll be honest with you, a lot of the videos, I mean, I've been learning LangChain for several months now, and when I started, we didn't have the LCEL syntax. We just had regular classes. And when they introduced that, it took me a while to figure it out. And what I find difficult is that a lot of the examples out there on the web are using the old syntax, which has been deprecated, okay, by the way. So now get with the program and you need to learn the LCEL syntax, okay? So once you do, let me instantiate my chain, and now you'll have to be quick because let me just make it a little bit smaller. And now if I run it, you'll see, let me clear the output, you should see it stream. See? It was pretty quick, but it's streaming, so it's working. Earlier I mentioned that I didn't like pulling the prompts from the hub, that I preferred hard-coding the prompts in my code for many reasons. The first one is that you never know what can happen to the prompt on the hub. They could delete it, they could change it, whatever. Also, it's a lot easier to fine-tune your prompt. For example, okay, here I did my own prompt. Okay, so just like the prompt pulled from the hub, I have my placeholder for my context and I have my placeholder for the question. Now all I need to do is format my prompt using from template. So I'm creating a template and I'm creating a custom RAG prompt using the from template method. Okay, then I'm reinstantiate my RAG chain. It's basically the same except that I'm changing the prompt. Okay, now let me run this. It's nothing new except that I'm using a custom prompt. Now here's another benefit. Let's say that I need to have the answer in another language, like in French, for example. I could change my prompt. Let me do that real quick. And I could say, or let me duplicate the chain not the chain, but the cell. Let me create a new cell. So you'll have the example on the GitHub. So let me change the prompt. And now I say, use the following piece of context like before, but I added answer in French and always say merci d'avoir posé la question. So thank you for asking the question at the end of the answer. And I added helpful answer in French. So now let me run the chain again, and I should get the same answer, but this time in French. See? So having the prompt inside your code makes it much easier to tweak your model. This is it for my first article of the series. Next week, I'll be publishing the second article on adding chat history. If you like the content of this video, please consider subscribing to my channel and liking this video. This really helps the YouTube algorithm promote my video to the proper audience. Thank you. See you next week.